Hello everyone, this is a SAP2000 tutorial, which we're using the latest SAP version 26.1 and considering to do a nonlinear pushover analysis on multi-story RC reinforcement concrete structures. So in this study, we will actually consider some modes. Additionally, like suppose that the first mode impact is what, and second mode, third mode. So then we will evaluate how the mode can be impact the response of the reinforcement concrete structures. So we jump to the program, but before that we explain our structure. The two bay, each bay is 8 meters and 5-story reinforcement concrete structure, and the column is 40 by 40 and the beam is 40 by 80, and the concrete we're using is 30 megapascal, and the steel bar is grade 60. So we will jump to the program and we take a new model. Actually, this tutorial can help for beginner and also advanced people who are intend to use a SAP2000. So we can use kilonewton meters and centimeters Celsius for the unit, and the material is going to be Europe. You can also use United States if you wish. So the type of modeling is a 2D frame. So here is called a portal frame. So later we will change the beam columns, or we can go the number of story 5, H story 2 base, H story IT 3, and length of the bay is about 8 meters. We can quickly go to the beam and we add a new property, and this still we're gonna use concrete and rectangular shape, which is C actually the depth is 800 and is B 400 by 800 or 800 by 440, and I'm going to give this one 0.8 and 0.4. Additionally, the material is going to be concrete 40 megapascal, so called add a new material, and you can use any country you want. So I'm going to use the material using China's material in the concrete and using C4T, which is equal 40 megapascal, and I can select again here. Additionally, we come to the section to modify the reinforcement concrete. So it's already grade 60, and the number of longitudinal bar is number 9, which is 3 one side, 3 one side, 3 one side. That's okay for a ordinary reinforcement structure. So I'm going to keep it okay. And the second is going to be take a copy of the same, and in this time we, instead of using B, we're using C, which is 30 by 30, and again same materials, same reinforcement, and this time is going to be a column and the previous one was beam. So we can come back again here and a little do modification, particularly here we call it beam. So the beam automatically will take the reinforcements. Now we can select its beam and its column, much more easier, and it's a 2D 5 stories, 1 2 3 4 5 stories. And additionally we go to the one of the XY views, and we're going to assign the joint restraint and it's be fixed. And the second is we're gonna define some loads. So we can assign dead loads and live load on the beams as a linear. But before that, we should define some load patterns. We already have this one dead load. We are gonna do one more live load, and we're gonna add. So we're gonna go to assign. We called frame load is a distributed load. So in the dead load, suppose we have 10 kilometers per meter, and we also select previous selection and change the live load, and the live load is 20. So we have totally two type of load. Now the second, before we go to the analysis, we should define some nonlinearity, because pushover is a nonlinear analysis. The second, when you considering the mood shape of the structure in the nonlinear analysis, so it's very difficult to determine the nonlinear hinges in the post-processing. So we will discuss about this also. So we go to the define. In the define section, we can come to the section and we define some hinge properties. So there is two type of nonlinear modeling. One is called distributed fiber elements, and the second is also concentrated indicated or LAM model. So we just consider the nonlinearities in the beam column connections or near this nodes, but also we can use fiber elements that considering the section is in a fiber way, model in a fiber way, which is entirely nonlinear. In a fiber model, it's a little bit computational, time consuming, but in the hinge technique, it's much more easier. So we do the hinge techniques. So it's concrete, and here you can see it's called frame hinge, and which type of behavior you want that the hinge should consider. So mostly this hinge will damage because of the significant moments, not actual force. So we will use moments, major moments in moment 3. Additionally, in some column there will be some actual force and also moment cost. So you can use PM2, PM3, and also we have fiber elements here, so we can consider the fiber. But the simplest way is this one, which indicate this direction is a moment and this direction is a rotational angle in that particular edges. So we define, this is very basically giving data is the points with the moments safety factors and also rotational safety factors. So this is the behavior of the hinge when the hinge is loading under the dynamic loads or any cyclic loads. So we will get this kind of curves, and also we can define some specific hysteresis behavior to this curve. So we have different modeling. So you can actually isotropic, kinematic, and tachyda, pivot, or concrete. So I'm using concrete, and you also can modify the parameters, so energy degradation factor as you wish. So 0, and also I can use 50, and which is between 0 to 1. So indicating how much the energy dissipation, the degradation should occur to this curve. 50% is like, this is the 100, and 50% will be here. And now if you're considering it's about 20%. So in some cases it will be 0, which means there is no degradation in this curve. Additionally, we can define the acceptance criteria for this reinforcement. For these things, you must check the ASC 41 code, which is for the retrofitting and improvement of the earthquake resisting structures. So this is a giving data which is equal to these parameters. You can see, yeah, it's positive, which is here. So if the D or this one reach to this one, which is going to be collapse, you can consider this a point. And I can keep it this one as a default, and you also can modify this one, or you can have a different beam columns, and then you can calculate this response. So okay, and I made the name it this one is for the beams. So I'm going to apply these edges to the beam. I can actually take a copy of the same things, and I can write it. It's called columns. And in this time, instead of using M, and I'm going to use this one, interacting PM, which is P is the axial force and M is the moment. So basically the column will deform or damage because of the significant axial force and also moments. So now you can the hinge specification should be based on the moment rotation or moment curvature. So moment rotational is again that we previously also defined for the beam. When you have a beam column connection and you do a cyclic load, and then you get the capacity of that beam columns. So, and also the moment curvature, the capacity of the section, and also the curvature of the section. We can consider different symmetry conditions. And we can modify these things by changing the parameters and also the acceptance criteria for the plastic deformation. So it's basically the same, but including the axial force as well. So you can see this is the moment and this is the rotational. So we can keep it this one as it is, or the symmetric. You also can change it, but the change can be based on the number of rebar that you have and number of the size of the cross section. You can calculate. So I'm going to keep it this one and okay. Now we have 2, and that's all. So we're going to assign those hinges to the come to frame to the beam column. So they come, it's called here, and then come to the hinges. So now you can understand the length of the hinge and the length location. So the hinge is going to be a nonlinear beam column. So it also have distributed elastic, and the location is going to be 0 here, and you must select the defined beam that you want. And the location can be changed from 0.2 meters, which is about here, or you can actually use a relative. So about 0.1% or 10% of the length of this beam. So this one is also okay. So I'm gonna apply. And the second is going to assign the hinges to the column, and so this is the column, and instead of the beam we select the column, and we're using the same procedure. So even you can actually use one single hinges in this point of the column as well. So okay, so we are done, and we can go back to the section hinges, and we can see how the hinges formed, how the hinge has the tail. So we're gonna call show, and we're gonna call generate. Here is the given hinge. You can modify, or you can actually double click, or just remember the name, and then later you can actually see the properties. So okay, And now we're basically done. And but before that, we're gonna go to the define some load cases. So the first load case is going to be let me the first is date load. We can do this one as a nonlinear. So we're gonna use a nonlinear date loads. So it's gonna be the initial condition is nonlinear. We don't have previous one. The second is going to also be nonlinear, and initial condition can be from date load, and the model is actually linear, not nonlinear, and we have two type of mode analysis. One is eigenvector and also range vector. So in this case, you can consider the stiffness from the live load, and the mass of the structure will be calculated from this one, which is we will modify. Additionally, it's a 5-story, so that maximum 12 mode is enough to get at least 90% of the mass participation. So here we must define acceleration point in a x direction. So we want the deformation only be in the x in the x-axis. So okay. We also can add a new load case, which is called pushover, and I'm gonna call it pushover. And here is a nonlinear static analysis. And additionally, you can consider some geometric nonlinearity. Yeah, it's very important. You can consider p delta because we have gravity load, so the gravity load will come to the columns. Some deformation will be because of the gravity load in the lateral part. So the masses we defined previously, and here we must consider acceleration or mode. So I will do two type. So I'm gonna using the acceleration in a first in a first direction, which is u1x, and we also do some additionally we can consider the initial condition is which come to the from live load, and after the dead load, the live load is solved. The initial condition will be from the live load, which the structure go push after the live load is applied. So we also modify these things, and here is called full load control or displacement control. In the displacement control, we have 5-story, which is about 50 meters. So the load monitoring is about 0.60, which is 60 centimeters in the top, and you can actually extend to 1 meters or more. It's going to be a later 1 meter. This is joint point 6, which is IHA. If you have any additional control displacement, you also can apply it, like wedge joint, this joint, or second floor, third floor. You also can do it, but it's out of the scope of this tutorial. So okay. Additionally, we will consider the result should be 7 amount of steps. At least minimum number should be 10 and maximum should be 100. So the nonlinear parameter has also impact to the time of the analysis and also the analysis result. So if you use some total steps, so we're gonna have 200, which we already giving 200 here. It should be 100. We're gonna call that 50 should be no steps. So even tolerance should be this one. We can make it smaller if you give the smaller. So the time will be time of the analysis will be increased, and the result will be changed. So the maximum event per step is 25. So basically it's okay. We can keep it this one in the default, and then it's okay. Now we're gonna make another nonlinear pushover analysis. We can copy of this one, which is called pushover mode. But in this case, instead of using acceleration displacement control, so we use a mode control. So we're gonna take the mode 1. You can give mode 2, mode 3 as you wish. So we're gonna first mode 1, and the displacement control is this one called mode steps. Same things, nothing has changed. So now okay. Additionally, we're gonna copy, and instead of this one, we're gonna call it 2, and we're gonna modify, and it's called mode 2. So the same thing's okay. We have now 3 pushover analysis. So we also can modify our masses. This is the mass. The mass should be come to the specific loads. So 100% the dead load and 25% live load. So this is a very basic recommendation technique for the mass considering in the dynamic or model analysis. Now we can save the model. Okay, we save the model as a pushover RC, and then we gonna run the analysis. So nonlinear analysis is actually completely difficult, and it's need a lot of time. But the structure is simple, so we can actually do it faster. And now the analysis completed. We can see the first deformation from mode 1, which the time period is 0.557, which is very close to the practical. And we go to the second mode. This second mode, which is bending, and this is, you can see, combined, and the foot is also complex, and we have that 5 mode. Now we come to here, and we want to see the pushover analysis. So you can say steps, also steps. So here is the first pushover, and the first pushover we have a beam slightly deformed, which is in the immediate occupancy. So we go to the second mode, and there is more beams is also damaged, and the column is also reached to the, so we have more, and step 4 also more and more. And first is the collapse prevention in the beams. So this is the last step, and we can also go to the display, and we call the plot show static pushover curve. So basically this in vice versa. To do this one, we can multiply by -1, then the direction will be changed. Or in the loading part, we give a -1 in the load case, so that will be. So I also can take, like here, go to display table. Yeah, this is the data, this is the displacement, and this is the shear force. So I can copy. Okay, I can actually copy, export table to Excel, and here is an Excel file. And I'm going to modify this one. So this is the displacement, and this is the shear force, and I'm gonna paste it here, and I can name this one as displacement based push over analysis. So what I'm going to do is I'm going to equal this one, so this one multiplying by -1. So, okay, now instead of this one, I'm going to copy this one, paste it here. just paste the number. So now what I'm going to do is I'm going to again uh, uh, come to here and draw a graph. Yeah, this is the pushover curve. So I can modify it by using change it here, at least using this one. Me use a okay, and okay, and I'm going to modify this one is being 0. If you remember, this here is a little not been 0 0 because the structure prior the initial condition was for live load, so we have that dead load and live load, and then that cost to should be out of the 0 0. So and I'm going to say this is the shear force. I'm gonna call it N as a kilonewtons, and this is going to be displacement as a meter. And here is so we don't need we don't need this border. We need to giving a border additionally. We don't need this one, and instead of this one I can name it displacement base pushover analysis. So I can take this here. We also can increase the thickness and the color of this one, and here is. So we finished the first one, and we go to the check back, so it's okay. We go to the second second analysis. So remember, the displacement and the force may be similar, but the idea of the hinge will not be appear. So we're gonna move pushover based on the first move shape, and you can see we don't have that's good things that we have move shape also. So we go to the first step, which is the same point, and the second we have totally we have 8. Yeah, in the mood analysis we have more steps, so we can see here the beams in the second floor is totally collapsed. So that's the 10, and we can go display the static pushover curves. So the first one was static pushover, the first one, and the second one is here. So it's a little bit weird because of the mood, and we can actually come to the file and display table, and we can take these two, or maybe we can also export to the Excel, and done. And we came to here, and here is the results, which is 12. Copy, and we come back to here, and we want to put it okay, and this thing is also can be here again, and copy, and this yeah, copy in, and this one is we called mood. Yeah, I can call it mood shape pushover analysis, mood shape based analysis. So I'm gonna using this one. Now again we change the graphs, multiplying by a -1 to change the to change the direction of the displacement. So here we can copy and we can call to, just a number paste. So this one is no need, and I can come back again, select, and this is called DBPOA, and another is we called MSBPOA, and X is here, Y is here. Yes. So this is the pushover. So remember, one thing is in the mood shape, because the mood of the structure is quite complex, and that cause, yeah, let me make it fix this one. Yes. So after because it's when the structure is in its first mode, so we can easily understand the structure is in a very let me go to the first mode. So if we go to the first mode of the model, mode 1, it is mode 1 which is already pushed. If I go to here, see it's pushed about 0.9, and then we using this one to push, because the mode is not uniform, so not uniform, and that caused the structure fail suddenly. And that's why we also consider that I mode and also evaluate the performance of the structure. So this is a very sudden drop, which means that one of the beam columns will be failed suddenly. And this is the point that we should consider in the design structure. But in the not in without considering the mode shape, so the structure will be like this. After one beam or column is filled, so the rest can be bear the structure, but the strength is lower. And now we go to the, but here is okay, similar. The capacity is giving the same. And if I go to the second mode, go to the here second mode, go to second mode. You can see the second mode is totally different, and we go in the top beam is actually deformed, because when we push the structure, when it's in the specific mode shape, or it's a bending or a sort of torsion, then the structure will be actually experience significant loadings. So like suppose that you have an element that's also already in a different in a slightly in an inclined shape, but you're going to push it, so it suddenly drop down. But if you have a straight line and you push it, so then it will be go like this one. So it's practically also applicable in if the structure faces to an earthquake or some sort of damage, and the structure show a slight deformation. In that after that deformation, you push it, the structure will collapse easily. Instead, if the structure is in static mode and then you push it, so that will be if you push to the elastic region, so it come back. If it's pushed further, then it will not come, and then the structure slowly fell, starting from the beams or column and then entire structure. So now in the second mode, we go to the display static pushover, and we're going to move to, and it's be much more different. So we can come to here, and we going to display, and we also go again export to the Excel, and it's the same 12 modes and 12 modes, but the result is quite close to the first one. So I'm gonna again I must come to chart design, and here is called add legend, and you can see, yeah, I'm gonna delete this one. It's the name of the. So what I'm going to do is I'm going to delete this part here, which is a negative, and that should be deleted. So this is okay for the. This is considering the first mode. And the other one is, which means totally the structure is collapsed after this one. And here I'm gonna paste it. I'm gonna put these things copy here, which is the similar. And I'm going to again multiplying this one equal this one multiplying by -1, and I'm gonna take a copy and paste it as a number. So again, I'm going to select the data, and I give a name. Again, I'm gonna give it mood shape based pushover analysis 2. So if I call that one is A1, and this one is called mode 1, and that should be mode 2. So I'm gonna edit, and I'm gonna take the X and going to be Y. So now you can see the result is a little bit different, especially with mode 2 is totally different. The structure showing much more stiffness, and in the first mode showing much more weaker, and additionally sudden drop after 0.5 meters. So this was the pushover analysis considering higher modes. You can also study the third mode, fourth mode as you wish, and this is the result. So if you have any question, you can put in the comment, and I will find time to answer you. So thank you for watching, and if you want more, please subscribe. And there is another tutorial that we will discussing on the weak and weak column and weak beam, or strong column, weak beam, strong column. So we'll have discussed those things in the coming tutorial. See you next time.